أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم السلام عليكم ورحمة الله. Welcome to the second lecture of this lecture series of our subject ME220 Manufacturing Process 1. So today we are going to start with this chapter number 10, which is the first chapter of CL1, that is the fundamentals of metal casting. So let's start with a brief overview of the casting technology. Casting technology dates back to 6,000 years, and it's a simple process in which molten metal flows by gravity or other forces into a mold, where it solidifies in the shape in the mold of the mold cavity. So we simply melt any material and pour it into the mold cavity and allow it to solidify. That's a simple mechanism for the casting technology. The first type of and it is the first type of shaping operation, if you remember the chart we saw in the last lecture, where we have the manufacturing process, which has the two subtypes of where we have the manufacturing processes, which has the two subtypes. The first one is the shaping process, then we have the assembly operations, we have the processing operations and the assembly operations. The processing operation has the shaping, and they have the property enhancement, and where they had the surface finishing. So the casting is the first step of the shaping operation, which is a solidification process. Most common type of solidification process are the casting and the molding. The casting and the molding are the common types of the solidification process. Although they are quite similar, but there are some differences between them. They have the similar phenomena or the mechanism that we melt the material and pour it into the mold cavity, allow it to solidify, but there are some differences between the casting and the molding. If you see here, they both have the molten material introduced into the mold cavity, allowed to solidify, but in the case of the casting, it is performed on metals, so due to low viscosity of metal, no external pressure is used to pour the material, so it flows by gravity, due to gravity. While in the case of the molding, which is performed on plastics or polymer, which have the higher viscosity, so they require external pressure for to be poured in the mold cavity. Casting mostly does not give the final product, while in the case of the molding, in a polymer material, we get the final products by the molding operations. In the casting, there is a possibility that mold can be used once. You have to break the mold every time, or it can be used multiple times. While in the case of the molding, mostly we have the mold that can be used multiple times. In casting, complex shapes are possible because we can make complex molds, and to get the product out of it, we can simply break the mold and get our product. But we have to use the mold multiple times, so we cannot make very complex shapes in a molding. We have to design mold in such a way that it can be open and closed easily to get the product. So these are very basic differences, very slight differences you can say, between the casting and the molding. So where we are standing here, we are starting from here. You have seen this graph, this chart in the last lecture. In the solid manufacturing process, we have the processing operation, assembly operation. Among the processing, we have the shaping, property enhancement, and surface processing. And we have all these types. And you have the joining, permanent joining, and the temporary joining processes. So now we are discussing chapter number 10. So that is from the processing operation, we move towards shaping, and from the shaping we move towards solidification, and among the solidification we have three topics: the casting of metals, we have glass working, and we have the processing of the polymer. So that is chapter number 10 of your book. It is, I guess, chapter 12. It is 10, 11, and this one is chapter 13. So CL1 includes this one and this one. It does not include this one. Okay, we are not going to discuss glass working because it has similar processes like this one. So we will discuss chapter 10, 11 and 13. So in the solidification we are starting with the casting of metals. That's fundamentals of the casting, metal casting, the name of the chapter. So let's start with it. What is the casting of metals? As you saw in the chart, the casting of metal has two types: expandable mold casting and the permanent mold casting. And there's further types of these two, expandable or the permanent mold casting. So we'll focus on the types of metal casting only, that includes expandable mold casting and the permanent mold casting, right? And we will discuss these types specifically, the further types, in chapter 11. We'll discuss this in chapter 11. In this chapter we're going to discuss only fundamentals. Okay, so casting include both casting of ingots and casting of shapes. Casting of shapes means we have some specific geometry. Ingot means any large casting that is simple in shape, like large cubes or large bars like this one. We have the large bars like this one. This one is the ingot, the large steel ingot. Okay. So casting can be used for casting of ingots, the large casting, or simple in shape, or casting of shape specific, like uh, gears can also be casted, and some other pipes, they can be casted. So they are specific geometries, and this is not any specific geometry. It will be further processed in some other mechanisms to get the final product. Now we will see some general advantages of the casting process and the disadvantages of the casting process. So the advantage of casting process includes it is used to create complex geometry, as discussed before. It is used to create complex geometry parts for both internal and external use. So we can create such parts with a complex geometry that can be used internally in any machine or externally for any casing, you can say. Some casting, there are some processes of the casting that can produce net shape. So we don't need any machining or surface finishing for that one. It gives very accurate dimensions. So there's some casting process that gives a near net shape, that is, no further operations are required to achieve the required geometry. Then casting can produce parts ranging from very small to very large size. In other machining, other processes, we cannot produce a large material or the very large size, but in the case of the casting, we will see in the lectures ahead, it can produce from very small parts, like as I said earlier, and the small gears, to the very large hammers, or the large you can say panels for the aircraft body, or the large slabs for the steel mill. Casting can be performed on any material that can be melted by heating. This is one of the greater advantage of the casting, because as you can see, there are other material forming processes like pressing or the punching or drilling. You need to have separate drill bits for other material, but for casting, any material which can be melted, it can be used in casting process. So this is one of the greatest advantage of the casting process, that any material that can be melted by heating, it can be casted in any shape. So you only have the greatest challenge in the casting is you have to melt the material. Then you can simply pour into the mold cavity, allow it to solidify. You will simply get the shape. Now, the disadvantage of casting process. There are certain disadvantages of the casting process that we need to take care of as an engineer. First one is limitation on mechanical properties. Why is that so? Because we get code structures, and I will tell you what the code structure in the next lecture probably, or the dendritic structure. That is it is talking about the microstructure of the material. It is talking about the microstructure like this. Okay. So these code or the dendritic structure limit the mechanical property of the material, and you will see in the next lecture how does it limit the mechanical properties. This is one of the disadvantages of the casting process. Second one is porosity. Due to non-uniform shrinkage while cooling, these pores act like a defect and stresses. So what happens when you pour, let's suppose you have the mold cavity and you are pouring a molten metal into the mold cavity and you're allowed to solidify, so it starts to shrink non-uniformly. So why? Because of that shrinkage, we have some air trapped here or here or here. So these pores, they act like a crack. They behave like a cracks in the material, like you can see here. This one, it is behaving like a crack in the material, like this one or this one. So these cracks are termed as defect or the stress razors. What happens? Let's suppose I have a material here. It has a pore. Let's make a larger figure. Let's suppose I have a material which has a small pore because of the non-uniform shrinkage, non-uniform solidification, and this material is used in any application such that it undergoes any force. Some force is being applied. So this force is being bared by the material. These are the force lines. But as soon as the force line comes here, they move like this way. So you can see the force lines are being concentrated These force lines are being concentrated at these edges of this pore. So maybe you are applying 10 Newton force here, but because of this concentration of force at these extreme edges of this pore, this edge might be experience a force of 15 Newton, right? So this is how it acts like a stress razor. This is how it acts like a stress razor. So that is why, and you as an engineer are under the impression that you are only applying 10 Newton, but you don't know because of the pore, the part deep inside is experiencing 50 Newton. So your part might fail without you determining the failure. Because you have calculated your process using the 10 Newton force, but because you don't know about the pore present deep inside, the material failed. That's why it's a really dangerous one in some cases, especially in the aerospace industry. Then we have poor surface finish. This is one of the general problem of the casting process. We have the poor surface finish. You can see here it has very rough surface. So this is very common problem of the casting process. Except in few processes we are able to control the surface finish, right? And then there's one of the common one, the safety hazard, because we are dealing with a molten material which might be of 700 degrees centigrade or the 1200 or the 1500 degrees centigrade. So there is obviously safety hazard to the worker, to the foundryman. I probably have told you that the factory that is performing the casting is called as the foundry, and the one performing that casting operation is called as a foundryman. Okay, the factory that is performing the casting is called foundry, and the labor that is performing those casting processes are termed as a foundryman. Okay, so these were just some basic advantages and disadvantages of the casting process. Now, some overview of the casting process. We have here the casting is usually performed in foundry, and the one performing the casting process is termed as the foundryman. The most common and the oldest type of the casting process is the sand casting. So this is used to demonstrate students the basic concept of the casting process. So it has almost all the components that are used in the casting process. So the first one, the casting begins with the mold. What is mold? Mold is simply a cavity to give the shape to the final part. It is the shape of the final part, and it is little bit oversized. There is an oversized cavity. So mold contains a cavity which determines the part geometry. Actual size of the cavity should be little oversized to have provision of the shrinkage of the material. Why it is oversized? So because once, let's suppose you want a part like this one as shown below. So this cavity should be larger than this one. So that when you pour the metal into this cavity and its shrinkage, it experiences the shrinkage, so it attains the final dimensions. It shouldn't be smaller than the final dimensions. Molds are made of a variety of materials like the sand casting, we have the sand, we have the plaster, ceramic, metals, and some other types. Right? Now, this casting process can be classified based on two things. Based on the mold, in the two ways. The first one based on the geometry of the mold cavity. Either the mold is open mold, you can see here it's an open mold, or it's a closed mold. You can see here this is also a mold cavity. This one is a mold cavity. Right? Open mold. What is an open mold? A liquid metal is simply poured until it fills the mold cavity. If you don't have any closing surface here, we simply pour the metal, and once it solidifies, we can break this mold and take out our part. While in the case of the closed mold, we have somewhat complex structure. We have a passageway called a gating system, and we will see what the gating system is. It allows the flow of molten metal from outside into the cavity. Okay, so for the closed mold, we have the closed mold here, and it is connected to outside up through a gating system, right? And we will see one by one what these parts are and what are their functions. So the first classification of casting based on mold was based on the geometry of the mold. Either it's an open mold or a closed mold. The second one is based on the mechanism one, how we are performing the casting based on the mold. We have the expandable mold casting. I told you it means once the part solidified, mold must be destroyed to take out the part. While in the case of the permanent mold casting, we can perform multiple casting in a single mold. So there is a mechanism of opening and closing the mold cavity to take out the part. The mold in which the molten metal solidified must be destroyed to remove the casting, commonly made up of sand, plaster, similar material with the help of binders. So if we are making mold from sand, so we need to add some binders so that sand can stick together and form a cavity. Other one, permanent mold, is mostly made of ceramic or the refractive material because it has to withstand the very high temperature of molten metals. So we have the casting process, which is classified based on mold cavity. Either we have the open closed mold, or we have the expandable or permanent mold. Sorry for this writing because I'm using this for the first time, so it will take some time for my hand to adjust with this device. Okay, so a casting, any type of casting, at the same time can be a closed mold expandable casting. A casting can be at the same time open mold, let's suppose permanent casting, or open mold expandable casting, or closed mold permanent casting. Let's suppose what is sand casting. As we saw in the last slide, the drawing we saw in the last slide, it was a closed mold expandable casting. Closed mold because we had a gating system, The mold was not open to the atmosphere. It was a closed mold and it was expandable because ultimately we have to destroy the sand mold to take out our product. Okay, this is how it works. Now, moving towards the next slide, we have now we will discuss each part of this general schematic of the sand casting. So you will find this diagram in your book under the section of sand casting. As we discussed earlier, it's a type of experimental mold casting. It is one of the most common type of sand casting and the oldest type of casting process. So in the sand casting, we have two parts. The upper part, that's called the cope. This upper part is called the cope, and we have the lower part, that's called the drag. Right? We have the upper part, that's called the cope, and we have the lower part, that's called the drag. Then the line separating these two parts is called the parting line. The line separating the cope and the drag is called the parting line. So sand casting, the structure of the sand casting, it has the upper part, the cope, and the lower part called the drag, and the line separating these two is termed as the parting line. Then we have something called pattern. We have something called pattern. In sand casting, mold cavities, now you must be curious that okay, the final product will be formed using this mold cavity, but how we will get the shape of this mold cavity? So we will get the shape of the mold cavity using the pattern. What is pattern in sand casting? The mold cavity is formed by pattern usually made from wood, metal, plastic, or any other material that has shape of the part of the cast. Thus, cavity is formed by packing sand around the pattern. So what we will do, we will fill this cope or the drag with sand. Then we will place pattern and allow it to make a cavity in the sand. And we will do the same with the cope one, and we will add some binder so that it takes the shape, and we will simply remove the pattern here from this cope and drag. So ultimately we have a vacant cavity here in the form of with the shape of pattern. That's called a mold cavity, and we will see in the video how to do that. Okay, now you know what the cope is, the upper part, and the lower part is drag. The line separating these two is called the parting line. We know what the pattern is. It is used to make the cavity of the mold. It is just a shape of the mold cavity. Then there's a thing called a core. What is core? Core is something that is placed inside the mold cavity to get the internal geometry. Let's suppose you want to make, if you see this mold cavity, what kind of shape you will get with the core? Probably like this one. Oh, sorry. Obviously it's not accurate, but like this one. It is solid part, and you can some vacancy here. So this is the purpose of the mold. So it is used to make the internal geometry of the part. So core is placed inside the mold cavity like this one. Then we have the gating system. Gating system is a pathway for flow of the metal. So gating system includes this pouring cup plus down screw plus runner. These all together makes up the gating system. Gating system. What is gating system? Gating system includes pouring cup plus down screw plus runner. This is the pouring cup. This one, this tapered one. This is a down screw, right? And this is the runner, the horizontal. The down screw is vertical one. Runner is the horizontal one that is leading towards the mold cavity. In casting mold, in a casting mold, it's a channel or network of channels through which molten metal flows into the mold cavity from outside of the mold. So what is getting system? It only allow a passage. It provides a pathway for a molten metal to reach the mold cavity. What is down screw? It's a screw through which molten metal enters the runner and moves into the cavity, and runner is the horizontal pathway into the mold cavity. We have the pouring cup. What is pouring cup? It's used to minimize splashes and turbulence upon pouring into the downstroke, and also controls, and you can see it is somewhat tapered with a larger diameter at the top and a smaller diameter at the bottom. It is used to control the volumetric flow rate, and we will see how it controls it. So we have the pouring cup, the initial one, and it is tapered to minimize the splashes and turbulence. Then the last one we are left with is riser. Riser is simply a reservoir. Riser is simply a reservoir of a molten metal to compensate for shrinkage during solidification. Right? So riser is before the mold cavity here. It's a reservoir that is formed. So once you start pouring molten metal, so this riser will fill up and we will leave it. So once there is a shrinkage here during solidification, so then obviously it will leave some space vacant. When it starts to solidify and starts to shrink, it will leave some solid space here. So the extra molten metal from the riser, it moves into the mold cavity to compensate the shrinkage and fill up the vacant space. So this is the purpose of the riser. Riser is a reservoir of the molten material to compensate the shrinkage in the mold cavity. And you must have a question that how it happens that riser is not shrinking itself while the mold cavity is shrinking and solidifying. So it's designed in such a way that the riser solidifies after the mold cavity or slower than the mold cavity, and we will see in the lectures ahead how does it happen in the riser design. So now we will see some demonstration video for this mold cavity and for the sand casting operation.
Recently, I decided to try my hand in making my own old-timey wheels. I started by making a 3D model in Rhino. The wheel will be about 6 inches in diameter, and it'll be super wide at 3 inches. I originally intended these wheels to be for a cart for the foundry furnace. I intended to have a 2-in-1 wheel pattern. If I wanted super wide wheels, I could use the pieces as a split pattern. If I just wanted...
So here he's designing pattern for the mold cavity in the modeling software. So this is basically a pattern designed for the mold cavity. So this is the pattern formation using the machining, and it is made up of wood.
The wood I'm using is 1.5 inch thick poplar, and it is a nice dense wood for routing something like this. To be able to sand both sides in relation to each other, I needed to temporarily glue them together. Here I am using Super 77.
So he made two parts of the pattern. One is for the cope, other is for the drag. So we can have the cavity in both in cope and drag.
Once all the sanding was done, I could re-split the pattern. I used a few coats of polyurethane to seal the surface. To find the center of any circle, you can draw an arbitrary line across the circle. Divide the line in half and draw a perpendicular line towards the center. Do this as many times as necessary until you feel confident that you found the center. Here I am using sodium silicate sand for the mold. I am hoping for a nice texture on the inside of the wheel to add to that old-timey flavor. After a few sodium silicate casts, I have found that actual mold release works better than talc for keeping the pattern from sticking to the mold. The texture of sodium silicate sand is a bit like mashed potatoes. I am adding screws here to help support the deep mold cavities. Here I am flash curing the mold with some CO2. This penetrates about an inch and gives at least a little bit of strength to the mold. Here I'll be using talc on the parting line, and I probably should have left a little bit more as it ended up sticking a bit. The best thing about sodium silicate sand is how forgiving it is. Small areas can be patched before the sand cures. Here I'll cut the gates and runners. And now I'll melt some aluminum. Here I'm degassing and removing the dross. Let's see how it turned out. Here you can see the old-timey texture that I was hoping for. I'll just need to cut off the gates and trim the parting lines.
As you can see here, this casted product has a really poor surface finish. So this is one of the disadvantages of the casting process.
I am using a bit of masking tape to keep the overspray to a minimum. I'll end up sanding the lip to get a crisp line. Aluminum primer will etch the surface and help the paint bond to the aluminum.
So this is the final aluminum alloy. So now we are done with the first section of this chapter, chapter number 10, Fundamentals of Metal Casting, overview of the metal casting. Now we'll move towards the engineering analysis of the sand casting. So this is the end of this lecture. I hope you have gained some basic knowledge about the casting process, and you have seen an experimental demonstration video for the sand casting. So in the next lecture we are going to discuss some engineering analysis of the sand casting. Should you have any question, you may reach me at the Google Classroom. Assalamu alaikum.